This video is for Math 1342, as we're about to learn Chapter 6. Chapter 6 is a concept called the normal distribution. Normal distributions, when you take a look at the way they look graphically, they're also famously known as a bell-shaped curve. And it turns out a lot of things naturally fall onto a graph like this. So when they do and they become normal distributions, then it makes calculating things a little bit easier when you know you have this kind. And even a lot of human measurements, like if you take many humans and measure either their height or their weight or their arm length or their hat size or their IQ, or testing ability, a lot of tests are built by normal curves like this. It turns out a lot of people are close to the mean. The mean is right in the middle of the graph. In fact, the mean, median, and mode are all right in the middle of the graph, but we usually work with the mean in this chapter. So the mean is the Greek letter mu. And then if you go one place left and right of the mean, one standard deviation left and right of the mean, so the way they write that is mu plus sigma and mu minus sigma. You might remember the empirical rule of chapter 3 remember that 60, 68, 95, 99.7 rule. It turns out about 2/3 of us will fall within one standard deviation of the mean in any kind of measurement you want to do on humans, or some things in nature fall this way too. So 68% are within one standard deviation, 95 are within 2, and 99.7 are within 3. Now in chapter 3, that's all you can do. You can either work between 1 and -1, or 2 and -2, or 3 and -3. But now we'll be able to go like between -1.8 and +2.7. We're not limited to exact values only, and we're not even limited to both sides being the same anymore. Here, the very first problem in the chapter 6 homework says a normal distribution is informally described as a probability distribution that is bell-shaped. See? So that's this B graph right here, bell-shaped. And I guess you could say this is an upside-down bell on this one. And this is more like a U shape, like a parabola. It does tail off down to -infinity up to +infinity, so it doesn't just stop like these two. But it's upside down like a bell would be, not this right side up version. Draw a rough sketch of the curve having a bell shape. So just so you know, it always looks like graph B. Okay, what requirements are necessary for a normal probability distribution to be a standard normal? Standard normal means that the mean is 0 and the standard deviation is 1. So I should add that on here. If there's different types of normal distributions, but the first one you learn is called the standard normal. The nice thing about the standard normal is you can compare ones that are on different scales then. In a standard normal, the mean is automatically 0 and the standard deviation is 1. So if they ever say standard normal, then you instantly know 0 and 1, or if they say the mean is 0 and the standard deviation is 1, then you instantly know it's a standard normal. So that's just another rule to know, and then they have a homework problem for that to keep that in mind, because you're going to do that on the next handful of problems every single time. Now, not everything in chapter 6 is automatically a normal distribution. There are other kinds as well. Here's one that says they're uniformly distributed. Uniformly distributed between 0 and 8. So just like in chapter 5, the main part of that chapter is the binomial, but not everything is binomial. Then we had another one later called Poisson. A similar thing happens here. The uniform distribution is not bell-shaped. When something is uniform, it means that it's the same throughout. So a uniform distribution, if they say it ranges from 0 to 8, you end up drawing this as a rectangle, basically. You just go straight across to 8 like that. So the height is always the same no matter where you are. That's why it's called uniform. Find the probability that a randomly selected passenger has a waiting time greater than 4.25 minutes. So the middle of this would be 4. And that would be the mean here too, because this graph is symmetrical. We want to be greater than 4.25. But the graph only goes to 8. This is not like the normal that goes all the way up to infinity. This literally stops at 8. So if you ask somebody if you know it's a uniform distribution, and if you know you're going greater than something, it's not really going to keep going greater forever. It'll stop at whatever the maximum is. So in essence, this is the same thing as asking between 4.25 and 8, since it stops at 8. And the way uniform probability is calculated, it's basically, there's nothing like in the graphing calculator that would help us do this faster, but it doesn't take too much. What you want to do is you want to do the range of the question. Remember, range is max minus min. So if I go from 8 minus 4.25, that's the higher number to the lower number that the question wants me to do. And then you divide by the overall range of the entire graph, which is, in this case, 8 minus 0. And I'm using the 8 both times. That may or may not have to be done. The bottom will always, in this question, the bottom would always be 8 minus 0. But they said greater than 4.25. Maybe another problem will say less than 3. Then you would go from 3 down to 0, and you would do 3 minus 0 on the top. Or maybe you want to go between 3 and 4.25, then you wouldn't use either the 0 or the 8 twice. It would just be used in the bottom. So the bottom's 8. 8 minus 4.25, I can do that in this calculator quicker. 8 minus 4.25 is 3.75. And then you divide by 8. 0.46875. Probably they're going to want me to round that. Round to 3 decimal places. Okay, so 469. Change this 8 to a 9. 469. So this is a minor part of chapter 6, but they're just, I guess the point of this is to let you know that not everything is normal. If you know you're in chapter 6, you can't just automatically assume you have a normal distribution. Uniform is another kind. Here's another uniform one. Now they want me to go between 48 and 58. So the numerator will be 58 minus 48. You just do the range of the question part. Range is bigger number minus smaller number. And then there should be an overall range down here at the bottom, 50.25 to 50.75. Oh, no, I have this backwards, sorry. The 48 to 58, that's the whole thing. That's like the 0 to 8 here. So the whole graph goes from 48 to 58. And then if you do 58 minus 48, that's the denominator for sure. You always do the whole range in the denominator. Then the numerator will either be greater than some number or less than some number or between two numbers. If it's greater than, you're going to go all the way up to 58 and do 58 minus whatever number they give you. If it's less than, it's going to be whatever they give you down to 48. But here it's between two numbers that are in between, literally 50.25 and 50.75. So the middle of this would be 53. 50.25 to 50.75, those are really close together. So the probability is this little area right here that's between these two numbers. I'm not going all the way down to 48 this time, or even up to 58, because they gave me two numbers to go between. But you always do the bigger one minus the smaller one for both the top and the bottom when you're doing a uniform problem. So 50.75 and minus 50.25. Think if you have $50.75 minus $50.25, you would get 50 cents back in change. And 58 minus 48 is clearly 10. But if you didn't know that, you could type it here. 50.75 minus 50.25 is 0.50 divided by 10. The probability of this is 0.05, which is 5%. So this area is only 5% of the entire graph. If you did the whole area of this whole rectangle, this is only 5% of it. 0.05. Now it said round to 3 decimals, but if it comes out to exactly 2, then I don't have to go to the third one. Okay, so that's probably it for uniform. They just threw that in there real quick to let you know not everything's automatically normal. But as soon as you see this, this is clearly normal because they have a bell-shaped graph here. And it does say standard normal as well. I always look for that because then that means the mean is 0 and the standard deviation is 1. Now, in this chapter, I shouldn't even say just this chapter, but in this topic, anytime you're doing any normal distribution at all, whether it's the standard normal or the ones we'll learn later, the phrase find the area and find the probability. Almost every question says either find the area or find the probability. They are synonymous in this chapter. Area and probability. In fact, I was kind of indicating that on the previous problem. We were really looking for the probability of the previous problem, but it's equal to area. You say this is 5% of the area or it's 5% of the probability. That's synonymous in this chapter. So I don't care if they say find the area or find the probability. Whenever they do that, there's a function in my calculator that will do this called normal CDF. Somewhat similar to binomial CDF, but a little bit different. Normal CDF, you have to put a smaller value first, a bigger value second, then the mean goes third, and the standard deviation goes last. That's the correct order. And if you're a typing type of calculator like this older version that I'm using, then you have to remember that yourself. If you've got a newer version, the ones that I call pasting calculators, then at least it reminds you of that order. It puts like lower limit first, then upper, and then mu, and then sigma. And once I know this is a standard normal, then whether they said this or not, automatically there would be a 0 and a 1 here. But they did say that too. So one of 3 things can happen, just like the uniform ones. They can ask you to go less than, or greater than, or in between. Those are the 3 kinds. This one wants me to go from 0.56 all the way down to negative infinity. In other words, less than 0.56. This is one of 3 cases. So if you're trying to do less than 0.56, you're really going between negative infinity to 0.56. Well, unfortunately, we don't have a negative infinity button in our calculator. But negative infinity is definitely smaller than any other number they would give you. So the bigger number is 0.56. And then you can trick your calculator into doing infinity or negative infinity by just putting a large enough number. Usually what's large enough is to put negative 999. So in the graphing calculator, press second vars. Maybe you remember how we up arrow to see the, if you up arrow, you'll see that Poisson and binomial stuff. But normal's right here. So the second option down, normal CDF. Turns out we never do normal PDF either, unlike binomial. Normal PDF calculates how high the curve is, and that's something in a like a calculus class might want to know how high a curve is at a certain spot. In statistics, we just don't need to know that. We don't ever do any problems that involve that. So the good news for us is we never pick normal PDF. It's just automatically normal CDF. If you're finding area or finding probability, you're doing normal CDF. We do use this inverse norm. That's the other half of the problems, but the normal CDF happens maybe 80 to 90% of the time. So I'm choosing normal CDF. Now I'm a typing type calculator, so I need to type negative 999, comma, 0.56, comma, 0, comma, 1. And then they want 3 or 4 decimals usually. So if it's 3, we're going to put 712. If they want 4, it would be 7123, because of that 6 would bump this second 2 up to a 3. So 712 or 7123, 4 decimals, so 7123. 7123. Here's a second case. Now we're going from negative 1.15 all the way to the right forever. So you're really going between negative 1.15 and infinity. And it still says find the area. Find the area. Or even if it said find the probability, that would be normal CDF. It's still a standard normal. In fact, the first 5 or so problems, maybe even more than that, will be standard normals. When you're in section 6.1, those are all standard normals. And the mean is 0, the standard deviation is 1. That'll happen in every standard normal problem. So here's a second case. A second case is when you go greater than. Then you do normal CDF. You put whatever number they give you first. Negative 1.15 is the smaller number. And the bigger number is infinity, so we put 999 for that, positive 999. And then 0 and 1. So anytime it's less than or to the left, you're going to go all the way down to negative infinity, and then you put negative 999 first. And then whatever number they give you goes second. Anytime it's greater than or to the right of some given number, then you put the given number first, then you put positive infinity second. There's nothing smaller than negative infinity. There's nothing bigger than positive infinity. So if you're ever putting a negative infinity, it has to be first. If you're ever putting positive infinity, it has to be second. And for all of section 6.1, you're going to put 0 and 1, third and fourth. But then once we get past 6.1, we'll put other numbers there too. So I need normal CDF, negative 1.15, all the way to 999. Second vars, down arrow just once to normal CDF number 2, negative 1.15, comma 999, comma 0, comma 1. And again, I did mention it briefly, but if you're a pasting type calculator, once you hit second vars and normal CDF, many of you will probably be pasting calculators out there. Every semester I get more and more people showing up with those because it's the newer version. But second vars, choose normal CDF. As soon as you press enter, you won't see what I'm doing right here on my screen. You'll be in a separate screen that says paste at the very bottom, which is why I call them pasting calculators. And there's 4 things for you to fill in. It's just a little more user-friendly. It says lower first. I think it says lower, like lower bound or lower first. And then you put the negative 1.15 there. You don't put any commas. Then you down arrow to the upper and put 999. Then you down arrow, although I think it defaults as 0 and 1 the first time you go in there. But if not, down arrow and put 0, down arrow and put 1, and then down arrow and press paste. Once you do that, you'll have this right on the screen here. And you just press enter again to get the answer. So the pasting people out there, it's just a little more user-friendly because it reminds you of the order, and it does the commas for you. I wanted to mention one more thing. People mess up negative signs a lot. There's a difference between this subtraction button on the side that's between the times and the plus. And there's negatives way at the bottom right next to the enter button. If you put a minus or a negative at the wrong time, you get an error message. It doesn't even do, or maybe it just does the answer wrong. So 8749 for this problem, 8749. Here's the final case when you want to go between 2 numbers. In fact, this is what normal CDF is built to do. I'm still trying to find the area. It's still a standard normal, but I'm going between negative whatever and positive what. It doesn't even matter if they're both the same or different in their pluses and minuses. Anytime you're going between 2 numbers, the smaller number is this one and the bigger number is that one, and the only difference is you don't need 999 of any kind. So this is just straight normal CDF with negative 0.91 first, positive 124 second, and then 0 and 1. So the between is the easiest case because you don't need to worry about is it negative 99 or positive 99. We won't use any of those. Normal CDF, negative 0.91. I forgot what the number was, 0.91. And then the upper number is 1.24. and then 0 and 1. And if you're a paster, go down and then hit paste. 7, 1, 1, 1. These are the three cases of normal CDF. Every problem in this chapter, well, I should say this, there's two major kinds of problems in this chapter other than that uniform distribution we already did. But anytime you're working with a normal, either you're finding the area of the probability or you end up doing the reverse process, which we'll learn in a minute. But in every problem where you're finding area or probability, there's three cases: less than or to the left, greater than or to the right, or between. That's the whole chapter. We do it over and over and over again. These three cases. So many people, by the time they take the test, even the quiz, they get good at knowing how to do normal CDS if they're using a graphing calculator. I should mention too, if you don't have a graphing calculator, there is a way to do these by hand with tables. See how it says click the table? You can click tables and look these up in tables. It's just two downsides to it is it's a little bit longer and harder to do it that way, and you don't get as exact answers as we get with the technology. But it is, if you want to read the textbook and see how they do that, if you like that better, you can do that. Okay, so I just did the three major problems of this chapter. We had a less than, we had a greater than, we had a between, but all three of them said find the area. Now it says find the z-score. And they're giving me the area. This is exactly backwards from these last three problems. So once you know you're doing normals and you're not doing uniforms, which most of the chapter is normal, there's only two kinds of problems once you're in the normal distribution. Find area or probability. They're synonymous in this chapter. That's when you use normal CDF. And there's the three cases. If it's less than or to the left, then you're definitely going to have a negative 999 first. And then whatever number they give you in the problem goes second. So the given value would go second. And then the mean and standard deviation are always third and fourth, even when they're not 0 and 1. But if you have a standard normal, they're automatically 0 and 1. And then you can go to the right or greater than. In both of these cases, they only give you one number in the question. It'll say like go to the left or less than 1.32, or go to the right or greater than negative 0.8, something like that. Then whatever given value you get, you put that first, and then you put 999 second. And the best case is the third one when you're going between two values. It's the only one where they give you two given values. And then you don't need any infinities to do this. You just put the smaller one first and the bigger one second. And you're technically doing that in the first two cases too. It's just that one of the two numbers is either negative infinity or positive infinity. Well, the other half of the normal problems is the reverse. In those problems, what's happening is they ask you to find area and probability, and you're getting a z-score or a raw score for an answer. I've said that backwards. They're giving you a raw score or a z-score to work with, and you're finding the area of the probability. Now the opposite happens where they give you the area or probability, and you're trying to find a z-score or a raw score. Or some kind of value sometimes, but it usually says find the z-score, find the raw score. This is the other kind. You want to use the third option that's called inverse norm. And it's called inverse norm because it's literally the inverse. It's literally the backwards version of the other ones. And this has three cases too. The best case is if you're going to the left. Inverse norm only needs 3 entry points. You put the given area first, and then the mean and standard deviation, which if it's standard normal, if you're looking for z-scores, then it's 0 and 1. Now, if you are a paster, you may also have another upgraded feature that some pasters have, but some don't. Another thing that started happening was a few years ago, people showed up with an even better feature for this inverse norm. Some people at the bottom, when they hit second vars and choose inverse norm, right down by where the paste is, there's an option to choose left, middle, and right, or maybe it says left, center, and right. If you have that feature, then you don't care which case you get. They're all equally easy to do. But left, center, right, or left, middle, I can't remember if it says center or middle. Then you can do all three of these equally. You just put in whatever area they give you, and you click the appropriate one that you're trying to do. But all typers and some of the pasters, I know there's some people that have these pasting screens for everything else, but they just don't have the option at the bottom to choose left, center, and right on inverse norms. Then you basically have to do it like us typers. If you get a case of the right, then what I usually do is I figure this out separately, and you have to do 1 minus the area kind of separately first, and then type it in with the mean and standard deviation, because it was built to go to the left. So if it's not going to the left, if it's going to the right, it's going the wrong way. You can change from the right to the left by doing 1 minus. That's kind of like the rain and the no rain complement idea. If it's a center area that they want you to find the z-scores for, and you don't have the option to pick the center, then you have to do 1 minus the area and divide by 2. Because 1 minus the area is both of the outside regions, and then dividing by 2 gives you both the left and the right. So in this homework problem right here, number 8, the graph shows a spot where there's a z-score I want to find, but the area to that is over here on the left side. So this is the best case for everybody. This is what inverse norm is built to do. I have a 9, 8, 4, 6 area or probability to the left of a z-score. Then what is the z-score right there? Find the indicated z-score around to 2 decimal places. That's exactly inverse norm. Whether you're a typer or a paster, whether you have the feature of left, center, and right or not, everybody's going to put this 0.9846 in. 9846. Typers would put that, comma 0, comma 1. Pasters would put 9846 in the slot where it says area, and then the other two should be 0 and 1 already. And then you just hit paste. If you do notice your calculator has left, center, and right at the bottom, just make sure it's highlighting left and click that one if it doesn't already have that one selected. But since I'm a typer, I have to do second vars, inverse norm, 0.9846, comma 0, comma 1. 2.16, because they just want 2 decimals. Usually they like probability rounded to 4 decimals and z-scores rounded to 2. And that way if you see something rounded to 4 or 2, then you'll know, oh, that must be a z-score, or that must be a probability. So it's just a technicality, but 2.16. Always read the blue part and do what they ask you to do, whether it's normally done that way or not. Now, see how it's shaded to the right this time? Now there's 8621 to the right. So if you have the type of calculator that has left, center, and right at the bottom of the inverse norm, then just type in 8621 for the area, and then put 0 and 1, and then click right. And then this problem's easy for you. The rest of us, we can't work with 8621. The rest of us, we need to know how much is on the left. Inverse norm was built to go to the left always before they added this newer feature. So if you're given the right, 8621, just 1 minus that first. 1 minus 8621. If you don't have the right option, you have to do this. But if you have the option to pick the right, don't do this. So everybody else has to use 1379 in their inverse norm. So I just have to figure that out ahead of time. 1379, 0, and 1. I'm not using the 86 number from the problem. Negative 1.09. And z-scores can be negative. That'll bother some people too, because area and probability can never be negative as an answer, but z-scores are negative half the time actually. Negative 1.09. And see how the Z line right here is a little bit to the left of 0? That kind of indicates it was supposed to be a negative answer, and it was. Okay, so then here's where we're between. About what percent of the area is between two z-scores, -1 and 1? So what this is doing, this is the final case when you're in between two. So, oh no, actually we're back to the other one. So I know what's happening now. So here's a z-score of -1. Here's a z-score of +1. They're giving me the z-scores and they want to know how much area is there here in between them. Find the area. That's normal CDF. So the first thing you got to get good at in this part of the chapter is, when do you know to do inverse norm and when do you know to do normal CDF? It all depends what they're asking you to find. Don't focus too much on a single word or symbol, because every problem in both versions, they either give you area and you find the z-score, or they give you a z-score and you find the area. So both of those words are in there. It's all about which one you're trying to find. I'm trying to find area here, so that's when it's normal CDF. And you do -1 first, +1 second, because I'm going between two. I don't need any infinities this time. And if you're talking about z-scores, z-scores are automatically standard normal, whether they say the magic word standard normal or not. So that would be 0 and 1 here then. So they did switch. You got to get ready for this, that they'll switch back and forth between, sometimes you're doing normal CDF, sometimes you're doing inverse norm. Now I'm back to normal CDF. -1, 1, 0, and 1. And I already know this answer because this is what you could do back in chapter 3. Remember back in chapter 3? How there was a 0 in the middle, and then you had 1, 2, and 3. -1, -2, and -3. In chapter 3, if they said between the -1 and the +1, or between the -2 and the +2, or between the -3 and the +3, those were these three memorized percentages: 68, 95, and 99.7. So this is between the -1 and the 1. This should be close to 68% here. See, 0.6827. So in chapter 3, they said memorize these numbers and they're approximately equal to these. See, it's not exactly 68%, it's approximately 68, because it's actually 68.27%. Or as a full, see, they do want the percent too. It says round to 2 decimal places. So I was going to put 0.68 in, but they want 68.27%. This is literally the empirical rule right here. They didn't just make that up to have students memorize something. If you go between -1 and 1, it's pretty close to 68. If you go between 2 and -2, it's about 95%. If you go between -3 and 3, see, here's where using technology, you can get quick answers really fast here, one after the other. See, 99.7. If you ever forget the empirical rule, like on the final exam, you can just regenerate it with normal CDF. 68, 95, 99.7. That's literally where it came from. But in chapter 3, you can only do these. You can only do the ones that are between -1 and 1 and -2 and 2 and -3 and 3. You can't do the ones that are like -1 to +2, or even -1.87 to 2.14, or anything like that. So here's -2 and 2. That's this one right here. 9545. If I round to 4 decimals, 95.45%. 95.45. It's really close to 95.5%, but in chapter 3, they just say approximately 95. And then when you go between 3 and -3, that's 99.7. And it's exactly 99.73 if you go out to 2 decimal places, 73. So all three questions, 9, 10, 11, and 12, 10, 11, and 12, those are they're just teaching where did those numbers come from in the empirical rule. They literally are calculations of the normal distribution. Okay, which of the following groups of terms can be used interchangeably? See, that's what I've been talking about too. Area and probability are definitely interchangeably. Area and probability. And because probability sometimes comes from relative frequencies, that's another one you could do. I don't think that comes up very often in any of the questions, but that's a third one technically. So area and probability are synonymous, and along with relative frequency. Areas and z-scores are not synonymous. In fact, that's the two different kinds of problems. Find the area or probability is one problem. Find the z-score, that's a different type of problem. That's the inverse norm. So area or probability and matched with z-score is definitely not synonymous. So areas and z-scores, areas, z-scores, probability, z-scores, those definitely are not matched up. Okay, so there's only 25 questions in this homework, and we've already done 13 of them. We've done more than half, just slightly more than half. And that was all 6.1 right there. We've only done one section. 6.1 is the essence of the whole chapter, especially after you get past those couple of problems about the uniform distribution. So there's 12 problems to go. They're all normal problems. And the good news is once you get good at section 6.1, then 6.2, 3, and 4 become easier to do. We're just going to make some slight adjustments each next section we go to. I'll go ahead and give you your magic word of the chapter right now. The magic word of the chapter, if you remember what chapter 4 and 5 were, this probably won't be a surprising answer. But let's go with Texans for this one. Send me the magic word of the chapter for chapter 6. And you should now have one for chapter 4, one for chapter 5, and one for chapter 6. If you send all three, you get 100 for that part of your grade. If you send two of the three, you get a 67%. And if you send one of the three, 33%. Otherwise, a 0. The only thing different in section 6.2 is that you won't have a standard normal. It won't be a mean of 0 and a standard deviation of 1, but the good news is not only are all the cases the same, but they have to tell you what they are. They tell you that the mean is 100 and the standard deviation is 15. So you just put those in instead of 0 and 1, but all the other rules you've learned so far are the same. So it says find the area. I have to decide, is that when I do normal CDF or inverse norm? Find the area, that's normal CDF. The picture shows it going to the left of 85, or maybe the question would just say find the probability or find the area of being less than 85. This is one of our three cases of normal CDF. When you go less than or to the left, you're going to go down to negative infinity. So I'm going to put negative 999 first, then the 85 that they're giving me second, and then I put 100 third and 15 fourth, rather than 0 and 1. Instead of just putting 0 and 1 at the end, now you put these instead. So you're actually working with raw scores now instead of z-scores. So this is second VARS, normal CDF, negative 999, since I'm going down to negative infinity, all the way up to 85. The mean is 100, and the standard deviation is 15. In fact, IQ scores, have you ever heard of the IQ test? The IQ test is designed so the mean is 100 and the standard deviation is roughly 15. It's not exactly 15, but it's pretty close to 15. So this is asking what's the probability that somebody would get an 85 or less on the IQ test? And the answer here is 1587. So almost about 16% of test takers would get an 85 or less on the IQ test. So 1587, 4 decimals, yes, 1587. That's the same thing we did in 6.1, except I just didn't put 0 and 1 at the end. Number 15, find the area. Same question, that's normal CDF. It still has a mean of 100 and a standard deviation of 15. Sometimes when you go from problem to problem, they'll change that, and then you got to readjust on those. But now the picture shows starting at 81 and going all the way up to infinity. So what's a chance somebody gets an 81 or higher on the IQ test? That's what this question is really asking. So now I need to do normal CDF, 81 to 999, and then you put the 100 and the 15 in the last two slots. 81 all the way to infinity. Find the area is definitely normal CDF. 81's the smaller number. 999's the bigger number. The mean is 100. The standard deviation is 15. 8973. There's almost actually 8974. There's almost a 90% chance that if you take the IQ test, you'll get an 81 or higher. Most people would get that high of a grade. 8974. I'm guessing the next problem is going to be a between. This will be the 3 cases of normal CDF all over again. See, between 95 and 120. What's the probability you'll get between 95 and 120 on an IQ test? Well, that's the best case of normal CDF. That's when you put the smaller number first, 95, bigger number second, 120, and we still have a mean of 100 and a standard deviation of 15. So this is where you don't need any 999 infinities. You're just going to do normal CDF because they're asking for find the area for the 3rd time in a row. Find the area, that's normal CDF. Go between 95 and 120. The mean is 100 and the standard deviation is 15. We had these exact same 3 cases back in section 6.1. The only difference was I just automatically put 0 and 1 at the end every time. 5393. Many students like chapter 6 the best of all the chapters because there's so few differences from problem to problem that if you start to catch the concepts, you can rack up a lot of points because there's not a lot of differences here. Not a lot of different rules to know or different things to memorize. 5393. And especially if you use a graphing calculator, then it really makes the calculations easy. Find the indicated IQ score. See, this one's not asking me to find the area. It's not asking for a probability. Those are normal CDFs. If they ask you to find a z-score or any other score, a raw score basically, see how they want the x. X is raw score. Before they put a z down here when we did a problem like this in section 6.1. So what score on the IQ test would put somebody where they're ahead of 99% of the people? This is like where are the super geniuses out there? What kind of score does a super genius get on the IQ test? Because here the mean is 100 and the standard deviation is 15. We're looking for the score this time and they're giving me the area. That's inverse norm. So, and it's going to the left. That's the best case of inverse norm. So inverse norm, you only need 3 things. You put the given area if it's going to the left, which this one is, 0.99. And then you put the mean and the standard deviation, which have been 115 for 4 problems in a row now. So the average IQ score is 100. This one should be significantly above 100 because you're ahead of 99% of the test takers. See, 134. 130. Now, this is a test score. Maybe they want me to round to the integer and say 135. There's actually a club called Mensa for super smart people. If you get 2 standard deviations above the mean, it's like 132. If you're 132 or higher on the IQ test, you can join this club of smart people called Mensa. So this person would be able to join the club because they're above 132 here. Round to 1 decimal place. Okay, usually test scores are integers, but we can still round to 1 decimal even if it is a test score. 134.9. So this person, if you get a 134, maybe you can get a decimal amount on the IQ test, or maybe that's just saying a little less than 135. So if you're a 135 IQ score, you're ahead of 99% of people. These are the Einsteins or the young Sheldons of the world, if you're into fictional smart people. Now, what if it goes to the right, though? See, this is still 115. Okay, so what IQ score, what score would put me at a spot where 0.2119% of people are better than me, smarter than me? So like about 80-some% of people are below me, but 20-some% of people are above me. What IQ score would make that happen? But the area is going to the right. So remember, that's the second case of inverse norms, is when it's going to the right, you have to 1 minus what they give you, unless you have the option to pick right in your inverse norm. So I just separately, before I even get to my inverse norm, I just do 1 minus whatever decimal they give me, 2119. If there's 2119 to the right, well then there's 7881 to the left. If you have a typing calculator, or if you have a pasting calculator that doesn't say left, center, and right at the bottom, you have to know how much is to the left if you're going to do an inverse norm. And if you do have left, center, right, then you don't need to do this step. You can just put 2119 in and make sure you click right instead of left. 7881. This is the second case of inverse norm. 0.7881, and then I can put the 100 and the 15. Inverse norm is just built to go to the left. That's all it can do. So you need to make sure you're going to the left until they created these newer ones that finally, that was actually a very good feature that they added recently, where you can pick left, center, and right, because a lot of people have trouble with this kind of question if it's not going to the left. 111.99. So if I round to the 10th even, that'll still be 112.0. Whole number, though. They want me to round to the whole number, so this is definitely 112. If you can get 112 on the IQ test, then only 21% of people are better than you. That's a pretty good score, actually. It's not a super genius, but that's a pretty good score. Okay, assume that adults have IQ scores normally distributed with a mean of 105. They're just making this up, but what if the mean was 105 and the standard deviation was 20? Just to show you that it's not always 115, but say you have a mean of 105 and a standard deviation of 20. Find the probability. You always want to focus in on what are they asking you to find. Almost everything in chapter 6 is find the area, or find the probability, or find some kind of score like a z-score or a raw score, IQ score, something like that. Find the area or find the probability. Those are synonymous, and that's when you do normal CDF for sure. This is definitely a normal CDF. And I'm trying to be less than 145. That's the first case of normal CDF. When you go less than or to the left, you go all the way down to negative infinity. So this, I noticed that this switched back to normal CDF because they said find the probability. I'm doing less than or to the left, so that's when you put negative infinity first, negative 999. Then I put the 145, the one given number to me. And then the rest is easy, because if it's not 0 and 1, they have to tell you what it is. So it's 105 and 20. Whatever they say those two are, you just put them in. So 9772, if they want 4 decimals, 9772. If you notice they're asking for 4 decimals, it's almost assuredly going to be a normal CDF problem. The inverse norms, usually they like them rounded to whole numbers or 1 decimal or 2 decimals, but the area and probability problems where they say find the area or find the probability, usually they ask for 4, and that's when you're doing normal CDF. Same thing here. Find the probability. They changed the mean and standard deviation. See, that's what normally happens, is each time you do a new problem, there's a new mean and there's a new standard deviation. But at least they have to tell you what they are. And now we want to be greater than 140.3. See, that's another case of normal CDF. We just did the less than case. Now here's the greater than case. The greater than case is when you go from the given number all the way up to positive infinity. So normal CDF, put this 140.3 first, and then put positive infinity after that. Second var is normal CDF because they want me to find the probability. I'm going greater than 140.3, so that definitely goes first, and then 999 goes second. And now they have different means and standard deviations than ever before, so I got to look them up again. The mean is 104.1. And, whoops, 104.1. Watch out for typos. And then the standard deviation is 24 exactly. 0657. Round to 4 decimals. Yep, 0657. Find the probability. Third time in a row. Find the probability. They switched the mean to 105 and the standard deviation to 15. But now here's the last case of normal CDF between 95 and 115. These last three problems, they just gave you the three cases of normal CDF all over again. But it was find the probability. That somebody might think this is a different problem, but it really isn't. So do normal CDF and start at 95 and go to 115. You don't need any 999 this time. And then you put the 105 third and you put the 15 last. 95 to 115. Normal CDF, 95, 115. The mean is 105. And the standard deviation is 15. 4950. There's a 1 after that, so it's going to stay 4950. 4950. We're still in section 6.2 right now. What conditions would produce a negative z-score? See, this is an important thing that students get bothered. Sometimes when they type something in the calculator and it comes out negative, they're wondering, did I do something wrong, or is this the case it can be negative? Area and probability answers, anytime they say find the area or find the probability, these cannot be negative. These have a hard limit. The answer is between 0 to 1. It's never negative. It's never bigger than 1. But if you say find the z-score or raw scores, well, z-scores can be negative. In fact, z-scores go from negative infinity all the way to positive infinity, although usually you go between -3 to +3 because the empirical rule, 99.7% of the time, you're between 3 and -3. So there is a chance, a 0.3% chance you could be beyond 3 or -3, but it doesn't happen very often. But literally, by the bell shape of the curve, if you put z-scores on this curve right here, the mean is 0. It goes 1, remember this from chapter 3, 1, 2, 3, and -1, -2, -3. It's literally negative half the time. Anytime you're below the mean, you're going to have a negative z-score. That's literally, I think that's what this question's asking, is when can you get a negative z-score? It happens anytime you're below average. If you're below the mean, you're going to have a negative z-score. If the average IQ test is 100 and you get a 90-something, you're below average and your z-score will be negative because of that. A z-score, what conditions produce a negative z-score? Anytime you're below the mean. So a z-score corresponding to a value located to the left. The left of the mean is below the mean, so yeah, this is B. Anytime you're to the left of 0, you're definitely negative. Okay. Oh, I guess we don't do section 6.3. Let's see here. Oh, yeah, I remember now. Yeah, 6.4. Oh, here's 6.3. Okay, I remember why I did that. Okay. So 6.1 and 6.2 dominate this chapter. Obviously, every problem we've done so far has been either 6.1 or 6.2. There's a little bit extra in 6.4, and then there's a little bit extra in 6.3. So 6.4, here's what happens. This is almost identical to 6.2, which is why I put it ahead of 6.3. The one difference now is there's going to be sample sizes that we never had before. Never in any problem from 1 to 22 did they ever mention anything about a sample size. So what happens when you include sample sizes? Then something slightly different, just like when you went from 6.1 to 6.2, there was a slight change there that you just didn't put 0 and 1 at the end anymore. You put whatever they told you they were. Same thing happens here. Everything you're doing here is almost the same. There's just one slight difference. So assume that females have a pulse rate that are normally distributed with a mean of 73 and a standard deviation of 12.5. This could be like the IQ problems that we did 5 or 6 of. If a female adult is randomly selected, find the probability that she is less than 79. So on this number 23 right here, it did say, find the probability. When I hear that, I instantly know that's normal CDF for sure. Find the probability. So just like all the 6-1 and 6-2 problems, you're definitely doing normal CDF. It said less than, or left of anything, you definitely put negative infinity first. This is the first case of a normal CDF. We want to be less than 79 beats per minute, so 79 is the given number. If it was standard normal, I would put 0 and 1 in these last two slots. It's definitely not a standard normal because they said the mean is 73 and the standard deviation is 12.5. So the only difference then is you put these instead of 0 and 1. So far everything's exactly like section 6.2. Here's the one difference. If they mention anything about a sample size, you have to divide the standard deviation by the square root of the sample size. They said one female was randomly selected. One adult female is randomly selected. That's a sample size right there. Now, it turns out the reason they have 3 parts here is in part A, they're going to say a sample size of 1. Part B is going to be a sample size bigger than 1. It turns out if the sample size is 1, the square root of 1 is 1, and anything divided by 1 is itself. So then it turns out it doesn't matter if you add the square root of 1 or not. But if it's anything bigger than 1, then you'll have to do it to get the answer right. And that's what's going to happen in part B. Part B is probably the exact same question as part A, except they're going to give me a larger sample size than 1, is my guess. So watch this here when I do it in the calculator. I'm going to do negative 999 and then 79, normal CDF, negative 999, then 79. The mean was 73 and the standard deviation was 12.5. If I divide, well, let me do it. I'll do it without the divided by square root of 1 first. There's the answer without it. But what if I hit second enter and now I can add this divided by the square root of 1 here. If I do it without the square root of 1, it said 6844. If I do it with the square root of 1, it's still 6844. So the point of that is if there's a sample of 1, then it's really the same thing as section 6.2. Then you don't have to do anything extra. 6844, that's why they have this part A here. They want to show you that if it's a sample size of 1, the rules are identical to section 6.2. But what if it's a sample of 25 females? And they did change, oh no, they got the same number, less than 79 still. So literally everything's the same except there's 25 females now. Now you have to put that or it'll be wrong. Now you have to do it exactly the same until the end. And now it's easy to forget to do this because the whole chapter you don't do it. But you have to do square root of 25. So watch when I change this to square root of 25, it'll make a difference in the answer. And since I've already typed it for square root of 1, I can hit second enter and not have to retype the whole thing. Back up on top of the 1 and just type a 25 instead. And look how the answer is not only different, it's a lot larger. 9918. 9918. It went almost up to 100% by adding 25 females. This was born from a case a little more than 100 years ago. There used to be really popular around the world. There was something called the World's Fair. Every year a city would host the World's Fair and it would move all over the world to different cities. At one of the World's Fairs, I can't remember if it was in the late 1800s or the early 1900s, this guy had a booth. Just like today you go to like a carnival and they have booths at carnivals and you can, if you're a vendor, you can buy a booth and if you make enough money that pays for the booth, then it might be worth it. And people have games, you know, those games where they have like little glass jars and you toss a ping pong ball and if it like goes inside of one of them, you win a stuffed animal. So this guy had a booth like that, and what his booth was, he filled a giant jar full of jelly beans. And he literally counted how many were in there. And it was in the thousands. It was something like 5,682 or some weird amount. But it was a very large amount of jelly beans. And you could pay $1. Now, back then it probably was a penny, but whatever the price to play was. Say you're paying $1 and you can guess. And if you're within a certain range of the answer, you win a stuffed animal. So people played all day long, and then he gave away some stuffed animals, but many people's guesses were way wrong. And many people lost. That's how you make money, in that a few people win, but a lot of people lose. So everybody's just doing it for fun. They throw away $1 if they lose, but then some people win. So anyway, one day he thought, why don't I write down all the answers all day long, because hundreds of people would play, and he would get hundreds and hundreds of different answers too. Some people would, it was like they were totally wasting their money. I don't know, maybe they had too much to drink or something, but there was clearly many jelly beans in there, and they would say like 23, but it was clearly way more than 23. Why are you even wasting $1? Or they would say 10 million, and it was not even close to what it actually was. But even with all the crazy answers, one day he took every answer, wrote them all down, added them all up, and divided by how many there were. And he was shocked to discover that even with all the crazy answers thrown in there, that the average would have won a stuffed animal. Many heads are better than one. That's where that expression, many heads is better than one, came out. If you pool a bunch of people together, you're much more likely to be successful. That's exactly what's happening here. With one female, there's only a 68% chance this will happen. With 25 females, it's almost a 100% chance. And that's what happened with the jelly bean example too. Why can the normal distribution be used in part B even though okay, so there's two rules. One is if the sample size is 30 or more, then you automatically get a normal distribution even if the original distribution is not normal. You'll see this rule a little bit more in future chapters too. See, they're referring to a rule in the book that if you have a sample size of 30 or more, then you don't need to worry about the shape of it, because it'll automatically be normal. But what if it's only 25? Then you can still do it if they tell you that the rates are approximately or just regularly normally distributed. If they tell you the population is normal, then any sample size works. But if you don't know the shape, or they tell you it's definitely not normal, it still works even if you have, as long as you have a sample size that exceeds 30. So we can do this because the original population was normal. They told me that. As long as the original population is normal, then any sample size works. But really, the part A and the part B, that was the good part about this problem, is shows you that many heads are better than one. Okay, so the standard deviation of the distribution of sample means is you have to take the standard deviation they give you in the paragraph, as always, but you have to divide by the square root of n. That's this extra step you got to do if there's a sample size different than 1. In essence, everything in section 6.1 and 6.2, you can basically think of all those that there was just a sample of 1. Because if there's a sample of 1, then you don't need to divide by anything. It turns out it's the same, with or without the square root of 1. But if you hear a sample size different than 1, you got to tack this on to the very end. It's sigma divided by the square root of n. It's easy to forget to divide by the square root of n to the given standard deviation, because most problems don't mention sample sizes. That's what 6.4 is all about. 6.4 is just what happens if there's a sample size, instead of just assuming you're working with the whole population. Now, I saved 6.3 for the end because this is kind of building up this rule about if an original population is normal, then any sample size will produce a distribution that is normal. Or if the original population is unknown or not normal, then you need samples of size 30 to get the distribution to be normal. So here, I don't know if this says that the population is normal or not, but we have 4 numbers, 45, 32, 22, and 16. And what if we're taking samples of size 2? Well, if the population is normal, then even samples of size 2 will be normal. Or if the population is not normal, then sample sizes of 2 would not produce a normal distribution. But what we can do in this problem here is what they want you to do is find all the samples of size 2. So let me do that over here. And I'm going to put the numbers in order first, because that can be a little confusing when they're auto order. So this is the last thing of chapter 6, and this is just a minor detail. You won't need to know this for the test, but this is trying to show you where this is called the central limit theorem, is what they're trying to show here. 16, 22, 32 and 45. So what if I take 16 and 22? That's a sample of size 2. Or I could do 16 with 32. Or I could do 16 with 45. Now maybe you can do 16 with 16. I don't know, does it allow you to use the same one twice? Yeah, apparently that's another one. 16 with 16 is another one. Okay, so see how they say that there are 16 of these. So what you want to do is start with one number, 16, write that down 4 times, and then include it with every number once. Then do the same thing with 22. 22 is going to get matched up with 16, with itself, with 32, and with 45. So 22 got all 4 of the numbers as well. Then go to 32. 32 will get all 4 of them as well. (16, 22, 32, and 45). And then finally 45. Write that 4 times and write it with each number once. 16, 20, whoops. 16, 22, 32, and 45. So then you need to find the average of each of these. Well, the easiest ones to do are when both of the numbers are the same. If both numbers are the same, then the average is that number. So the average of 16 and 16 is 16. The average of 22 and 22 is 22. The average of 32 and 32 is 32. And the average of 45 and 45 is 45. For all the rest, we just have to add them up and divide by 2. So if I want to average 16 and 22, that's 16 plus 22 divided by 2. That's a 19 average. 16 plus 32 divided by 2 is a 24 average. 16 plus 45 divided by 2 is a 30.5 average. Now, if you do one backwards, it's the same. 22 and 16 is the same as 16 and 22, so that's 19. 22 plus 32 divided by 2 is 27. Well, that means when it's backwards, 32 and 23, that one's going to be 27. 22 plus 45 divided by 2 is 33.5. Now, I did have a 16 and 32 already, so 16 and 32 is 24, so the other way around is also 24. I had a 22 and 45, that's right here backwards, so that's 33.5. I had a 16 and 45, so here's 45 and 16, that one's 30.5. So every one of these is happening twice. So once I do 32 and 45, the backwards version will have the same answer. 32 plus 45 divided by 2 is 38.5. Okay, so now what you do here is for each of these averages, you want to put in something over 16. There were 16 of them. How many times did the answer equal 45 for an average? There was only one time that the answer was 45. So that's literally 1 out of 16 of a probability. 1/16th, unless they want decimals. Let me check. Type integers or fractions. Okay. How many times did 38.5 happen? Once, twice. 2 out of 16. I don't know if they want it reduced. I'll just leave it 2 out of 16 for now. That could also be 1/8. 33.5 also happened twice. 2 out of 16. 32 once. Yep, just once. 1 out of 16. 30.5 once and twice. 2 out of 16. See, some answers happening once, some are happening twice. Now 27. Once, twice. 2 out of 16. Oops. 24. Once, twice. 22 is once. 19 happened twice, and the 16 only happened once. 19 happened twice. 16 happened once. I've used all 16 of them now. Unless they want them reduced. No, see, they took them unreduced, so that's fine. Compare the mean of the population to the mean of the sampling distribution. Okay, so the mean of the population is easy. Just take the 4 numbers, add them up, and divide by 4. 45 plus 32 plus 22 plus 16 divided by 4. The population mean is 28.75. Well, what's supposed to happen is it's supposed to equal the mean of the sample means. It's supposed to be equal to 28.75. So I guess the way we would tell that is this is a probability distribution. So if I put this into the graphing calculator, we can do like we did back in chapter 5. If you remember the very beginning of chapter 5, you put the x's in L1 and you put the probabilities in L2. So what if I put 45 with 1/16? Well, let me put all the x's in first, actually. So 45, 38.5, 33.5, 32 and 30.5, 27, 24, 22, 19 and 16. Sorry, 19 and 16. There's every x value. And now we can put all the probabilities. Every single one of them is either 1 out of 16 or 2 out of 16. There are only 4 that are 1 out of 16. So it's 1, 2, 2, 1. 1 out of 16. 2 out of 16, 2 out of 16, 1 out of 16. The bottom one's 2 out of 16 in this first column. Then the second column is 2, 2, 1. 2 out of 16, 2 out of 16, 1 out of 16. And the last 2 are 2 and 1. 2 out of 16 and 1 out of 16. So then remember how to find the mean of the probability distribution. You go to Stat, Calc, 1var Stats, and if you're a paster, you might have to trick your calculator by getting it wrong first and then do second enter, so that way you can type L1, L2. The mean's supposed to be 28.75, so when I press enter, that should be the X bar. See, 28.75. Somebody discovered this, that if you put every possible sample possibility and do a probability distribution of it and find the average or the expected value of the probability distribution, it always equals the population average too. That's part of the central limit theorem. And you remember that section 6.4 problem where the standard deviation gets divided by the square root of n, but the mean didn't change. We didn't do anything to the mean. This is why. The mean of the samples will always equal the mean of the population. But turns out the standard deviation, it's not exactly equal. You have to divide by the square root of n. Do the sample means target the value of the population mean? I guess it would, because they're equal to each other. In general, do sample means make good estimates of population means? They do. That's why we work with sample means in statistics, because they are unbiased. Random samples are unbiased. Okay, so there's everything in chapter 6. This last problem takes a while, but the whole point of it is to try to convince you of this problem that we last did before this one with the females. You see how when I did it with one sample versus 25 for a sample, when the sample size is 25, the standard deviation gets affected by that. But the mean doesn't. See how the mean stayed the same? That's the point they're trying to make here. That if you're doing a problem that's basically with no sample size, whatever the mean is, it stays the same even when there is a sample size. That's exactly what happened in this final problem. So this was the video for chapter 6,